In this video, we'll go through an IB question and it'll end up with us calculating the rate constant for this reaction here. So here's our reaction, and this is the data from the experiment. We have 4 different experiments. We have the initial concentration of the nitrogen monoxide, initial concentration of the hydrogen, and the initial rate of reaction. So part A, determine the order of reaction with respect to hydrogen and with respect to nitrogen monoxide. So we'll do the nitrogen monoxide first. Now, just like in the previous video, you look for 2 experiments where the concentration of the one you're trying to find is changed and the concentration of the other reactant stays the same. So in experiment 1 and experiment 3, we are doubling the concentration of the nitrogen monoxide and the concentration of the hydrogen stays the same. And the rate increases by a factor of 4. So we'll do the hydrogen next. And for hydrogen, experiment 1 and 2, we double the concentration of hydrogen, the concentration of nitrogen monoxide stays the same, and the rate doubles. So for hydrogen, we've doubled the concentration and the rate doubles, so it's first order with respect to hydrogen. And for the nitrogen monoxide, we doubled the concentration and the rate increased by a square of the change, which is 4. 2 squared is 4, so it's second order for nitrogen monoxide. So in part B, write the rate expression for the reaction. So we write rate equals K, and then we have the concentration of the nitrogen monoxide raised to the power 2, and the concentration of the hydrogen, and that's the rate expression for the reaction. So it's second order with respect to the nitrogen monoxide and first order with respect to the hydrogen, and overall it's a third order reaction. So finally, part C, calculate the value for the rate constant and state its units using the data from experiment 1. So here's experiment 1. We're going to use this data here to calculate our rate constant. So we write our rate expression, which is rate equals K, concentration of the NO to the power 2 times the concentration of the hydrogen, and then we input the values from experiment 1. So the initial rate is 2.53 times 10 to the negative 6, which I've put here, and that equals K, and the concentration of the NO is 0.100, which I've put here, squared to the power 2, and then multiplied by the concentration of the hydrogen, which is 0.100, which I've put here. And then I've rearranged the equation to get K equals this, and that gives me 2.53 times 10 to the negative 3, and the units are moles to the negative 2, dm, decimeters to the 6, and seconds to the negative 1. I'm going to go through how to calculate these units next. So here we have another example. It's nitrogen monoxide reacting with hydrogen to form nitrogen and water, which is the same reaction as the previous example. And you have to deduce the order of reaction with respect to nitrogen monoxide and hydrogen and explain your reasoning. So again, you choose the experiments where one reactant is changed and the other stays the same. So I've chosen 1 and 2. The concentration of the nitrogen monoxide is doubled, the hydrogen stays the same, and the rate increases by a factor of 4. And then for 2 and 3, the concentration of the hydrogen is doubled, the nitrogen monoxide stays the same, and the rate doubles. So it's second order with respect to nitrogen monoxide, and the reason, because you have to explain your reasoning, is double the concentration of NO, nitrogen monoxide, the rate increases by a factor of 4. So that means it's second order with respect to NO. And it's first order with respect to hydrogen. So you double the concentration of hydrogen, the rate increases by a factor of 2. In part 2, deduce the rate expression for the reaction. So rate equals K, concentration of nitrogen monoxide to the power 2, multiplied by the concentration of the hydrogen. Okay, so now on to part 3, determine the value of the rate constant for the reaction from experiment 3 and state its units. So I've written the rate expression here and I'm going to substitute in the values. You have to be a little bit careful because it's 10.00 times 10 to the negative 3. So always check for the units at the top. Okay, so the initial rate is 10.00 times 10 to the negative 5. So that's why I have it here. So I start with 10.00 times 10 to the negative 5 equals K, and I have the concentration of the NO to the power 2 multiplied by the concentration of the hydrogen. And I'm going to cancel out for this side, so I divide both sides by the product of this, so it's 4.00 times 10 to the negative 7, and I do the same for this side, and I get K equals 2.50 times 10 to the 2, and the units are moles to the negative 2, decimeters to the 6, and second to the negative 1, and I'm going to explain how to get the units next. Next we look at units of K. So for a zero order reaction, the rate is equal to K. And the rates for a zero order reaction are the units for rate. And here's the units for rate of reaction. It's mole per decimeter to the negative 3, second to the negative 1. So that's for a zero order reaction. Next is a first order. So the rate is equal to K times the concentration of A. So K equals units of rate divided by units of concentration. So the units of rate are moles per decimeter to the negative 3, second to the negative 1. And the units of concentration are moles per decimeter to the negative 3. Well, those two cancel out to leave you with seconds to the negative 1. So for a first order reaction, the units are second to the negative 1. Next is a second order reaction. The rate is equal to K times the concentration of A to the power 2. So K equals units of rate divided by units of concentration squared. So we got moles per decimeter to negative 3, second to negative 1, divided by moles per decimeter to negative 3 squared. And when you cancel out, you're left with mole to the negative 1, because you bring the mole up from the bottom, so it becomes negative 1, dm decimeters cubed, seconds to the negative 1. And finally, for a third order reaction, rate equals K times the concentration of A to the power 3. So K equals units of rate divided by units of concentration to the power 3. So it's moles per decimeter to negative 3, second to negative 1, divided by moles per decimeter to negative 3 to the power 3. And when everything cancels out, you're left with mole to the negative 2, because you should have 2 mole left on the bottom. And then decimeters to the 6, because there should be 2 decimeters left on the bottom. And then the top will cancel to leave second to negative 1 on the top. So you end up with mole to the negative 2, decimeter, 6, second, negative 1.